So, welcome back student. So, in our last class we learned something about orthogonal basis and find something called Fourier coefficient. So, let me write once again these things. So, f x can be represented, I do not write the equal sign right now here. So, let us write the nearly equal to sign, say C I phi I x and I. F x is a function, I want to write this function, I want to decompose this function in terms of some linearly independent set of function phi I which are orthogonal to each other, and if I do that then I want to find out what is my C I. That calculation we have already done in the last class, but today what we are doing that we try to find out what is the error and how the minimization of the error can be calculated. So, minimization of the error will come with this C I. So, if I adjust my C I in such a way that this error can be minimized for a given set of function, then readily I can understand what is the value of C I. So, let me say E is a error function which is f x minus this quantity. Please note that since f x is not equal to this, so error has some value. So, that means error function is something here, it is not equal to 0, since I am saying that this is nearly equal to 0 or it is of the order of these things, but not equal to f x completely. So, that means there is some error associated with that. So, let me write this function f x, and we have some function here also which is a linear combination of these things. Say I write this function as my p x is a function where p x is summation over C I phi I x I. Now, E function is given by this minus f x, the given function, minus p x, another function which is a linear combination of the set of functions which is orthogonal to each other, we called it basis. Now, if I want to find out what is the inner product of E by E, that means what is the norm of E, what is the magnitude of E. So, I will have to do this operation which is essentially A to B, this quantity multiplied by this quantity. So, it is something like this, this quantity is this, I try to find out this quantity which I call say delta, which is a number. This delta is a inner product of the error function, that means delta give me the value or the norm of the error function. If I do that, then the right hand side I will have this. Okay. Now, I want to minimize this quantity. How I minimize? Which is the variable here? Which quantity is variable here? F x is a function that is given, fine, and p x is another function which is given by this. Now, this is the basis function, it is already given. So, I am not going to change that. So, what thing I want to target? I want to target that how I fix my coefficient C I so that this error become minimized. So, that gives me readily what is the condition or what value of C I should be there to minimize the error. If I do that, then I need to find out this quantity. So, in order to minimize the error with respect to C, I need to find out this quantity. The way we find a minimization, the function is minimized, so I need to make a derivative. Here C x is a changing thing, changing parameter, so I need to do that with C x. If I do, then the right hand side has something like 2 f x minus p x, derivative of these things over C x. So, 2 of these things multiplied by this and derivative of this quantity. with a negative sign. So, minus this quantity, if I do from that notation, whatever we have, del p x del c k is what quantity? It is a summation over that. So, one c k is here sitting, and when I make a partial derivative over c k, I will only have phi k in my hand here. So, this quantity, again this quantity is 0, because I know that this is minimized. So, in order to minimize, I need to this is my condition that should be minimized. So, finally, I will have a to b, these two will be cancel out, I mean this 2 and this minus sign will be absorbed, because left hand side right hand side is 0. So, I will have f x minus p x, this quantity I already find out, which is phi k. Is equal to 0. This equation I have. Now, if I put that one by one, then I will have something. So, then I will have a to b f x phi k x dx is equal to a to b phi k x multiplied by p x. P x I will put this. So, summation of I c I phi I x, this. Now, left hand side is f x multiplied by phi x dx a to b. It is nothing but the inner product between the phi k and f. So, I write it is phi k and f in inner product notation. This I can write in this way, no problem with this. Then what I will do? I will take the treatment, the logic of the treatment is exactly same. Okay, 1 dx should be sitting here. So, phi I x dx. I take this summation sign outside, C I is not there. So, I can put this inside, the integration inside, where this function is associated, and I can write this. So, now this quantity, you can readily understand what is the meaning of this quantity. It is C I, this quantity is nothing but delta k I mod of say I square. This. Now, if I run this summation over this quantity, then this quantity simply comes out to be C k mod of phi k square, and my C k comes out to be phi k f this quantity we have already figured out in our last class, the same quantity, but here we show that this is the Fourier coefficient, and if I want to find out the minimum error, then for the minimum error the coefficient should naturally come in this form, and if this form are there, then we can say the error, associated error, when I expand a function in terms of the set of orthogonal function phi I, the error will be minimum if my C, if I choose my C in this way. So, this is the natural choice of C to minimize the error. Okay. So, next is something very important. After having this knowledge and all these things, now we are in a position to write something which is the Fourier series. So, in Fourier series, for example, I have a set of function which is something like this. So on. This is a set of function, infinite set of function, and in some previous class we already showed that these functions are linearly independent to each other, that is point 1, and also they are orthogonal to each other. By the way, this function is belongs to this set, continuous set of function with the limit minus pi to pi. So, for this limit, whatever the function is given is linearly independent to each other, that is point 1. Second thing is that they are also orthogonal, these functions are orthogonal to each other. Now, I know a set of functions which are orthogonal to each other, orthogonal functions. So, any functions can be represented in terms of this set of functions according to whatever we have learned so far, this knowledge. So, I write this in this way. The same thing, this is nothing but if you consider f x, this is the same thing by writing this quantity. I am writing the same thing, but by splitting 3 parts. One is associated, first part is associated for this 1, the function which is 1. In this case, what happened? My function was given as phi 1, phi 2, phi n, and so on. So, in general, I write in this way. This is a summation form I write. This form and this forms are eventually same. Only thing is that I divide this sine function with another one summation and cos function with another summation, with some coefficient associated with the sine A and some coefficient associated with the sine cosine, we call it B, with some indices, exactly like I just change the indices, the same thing. Now, if I have this, now readily I know what is my coefficient this. So, what will be my, there is a reason why I put 2, we will check that. What will be my A2 by 2? If you remember, let me write it here once again. What we find just few minutes ago, that if the function is represented like this, my Ci will be the inner product of this quantity divided by the norm of this quantity, that I figure out. This is the Fourier coefficient. So, I am trying to find out this coefficient, which are the Fourier coefficient. So, A0 by 2 will be represented by this divided by this. So, this means what is the function associated with this coefficient 1 multiplied by whatever the function is given to me. When I am taking the inner product, it is minus pi to pi. This is the definition of this, divided by norm of this, that means minus pi to pi 1 into 1 dx. This. So, my A0 will come out to be simply this quantity is how much? 1 dx integration of minus pi to pi. So, it is 2 pi. So, 1 by 2 pi integration minus pi to pi, this quantity. Here I should write a dx, f of x dx. Fine. So now I know what is my a0 coefficient. If my function is given, then I just integrate, and then if I calculate this, I will find what is my a0 by 2. So my a0 is, I should write it here, a0 is 1 by pi integration minus pi to pi, whatever the function is given to me, with dx. First coefficient I calculate, and which is something like this. Now what about the other coefficients? Again I want to find out an coefficient. So an, applying the same thing, that means the function associated with an will be linearly, will be the inner product of this quantity. So minus pi to pi, whatever the function I have, I need to multiply it with sin nx dx. This is nothing but the inner product of this function with sin x divided by integration of minus pi to pi sin square x nx dx, this quantity. If the function is given, I can calculate this, but this I can readily calculate. How to calculate that? So this part, only this part. So it is, if I take half here minus pi to pi, then it will be 2 sin square of these things. That means I can write it as 1 minus of cos 2 nx dx. 1 is sin square theta plus cos square theta minus cos square theta plus sin square theta, it will be 2 sin square theta, this quantity, because there is a half sign sitting here. So now if I do the integration, it will be half, this integration is something, okay, let me do that meticulously, minus half integration of minus pi to pi cos 2nx dx. This I know what is the value. This is half into 2 pi. What about this quantity? This quantity is minus of half, cos will be, when I integrate the this cos, then what happened? It will be sin of 2nx divided by 2n with minus pi to pi. Now we know that whatever the value here we put, because this is a sign, so if I put pi here in place of x, so this will going to vanish. So eventually what I will have, that this quantity is nothing but pi. Contribution of the first term. So once I have this, so I can readily find what is my an. So my an is 1 divided by pi integration minus pi to pi fx here, but here I should have fx into sin x. So fx into sin nx dx. So also I will find what is my coefficient, Fourier coefficient an. In the similar way, exactly the similar way, I can also figure out what is my bn. Let me do that meticulously, so that bm should be integration of minus pi to pi inner product of fx into cos mx dx divided by norm of this quantity norm square. So, that means integration minus pi to pi cos square mx dx. Again, this quantity I need to find out once I have the value of fx. So, when the value of fx is given, then only I can calculate that, but here this quantity I can find out readily. This quantity exactly in the similar way, if I make a half minus pi to pi, then this half gives me 2 of cos square this quantity, which is 1 plus cos 2 of mx dx. These things. Again the same procedure, half integration minus pi to pi dx plus half of, let me do the integration here, cos integration is sine of 2mx divided by 2m with the limit minus pi to pi. If I do this limit, if I put this limit again in the way I find in the previous case that it is 0, here also it will be 0, because sine of pi and sine of minus pi both are 0. Sine of n pi, whatever the coefficient here we have, we shouldn't bother. So, here we should again have something pi. So, I can write clearly, let me write it here, if I can expand a function in terms of sine and cosine series, which is a orthogonal function in the range minus pi to pi with 1. If I write this is an expansion of a function, then I can find the Fourier coefficient here, and the Fourier coefficient for this is a0 should be 1 by pi integration minus pi to pi f of x dx. A n is 1 by pi minus pi to pi, whatever the function I have multiplied by sin nx, and b of m is 1 by pi minus pi to pi fx cos of mx dx. So, all the coefficient I know. Please note that there is, I put it here m, I put it here m. So, this n and m has the same, they just suggest that they are the coefficient of some order. So, this is 1 2 3 4 5 6, here also 1 2 3 4 5 6. In some books both the things are same. So, no problem with that, we can also write it as bn is equal to cos of n. So, it will not going to change anything, that does not matter whether you are putting, but just to make the difference that this is a series of sine series, this is a series of cos series, I just put this integer different in name here, but you can also put n here because I have already put b. So, it is a different from a. So, you can also put and do the same thing, nothing will going to change. Okay. So, now I know what is the Fourier series and how the different coefficients are related to each other. These coefficients I can figure out when the function is given. Sometimes what happened that the function is given in the range, for example, minus L to L instead of minus pi to pi. Then the Fourier series something will be same. So, the function of fx will be represented, mind it here, now the function is changed to, the limit of the function is changed to minus L to L, not the pi. So, that means L is tends to pi x will be changed as this quantity. So, whatever the, when we put the value x here, when the limit is minus pi to pi, when it is L, I need to put in terms of, in place of x I need to put these things. So, f x, let me write it. F x is a0 by 2 a n sin n pi by L x. I can't write sin n x because my limit is minus L to L. Please note that when L is x is L, then it is come to n pi. So, I just rescaling this quantity plus m bm cos m pi L multiplied by x. Sometimes the limit is given in this way in some problem. We will try to target few problem where this kind of limits are given, and then the structure will be this, and then a0 will be something like this. An will be represented by this, and Bm will be represented like this. It is the same thing, the previous case, whatever the thing we have done here, we are doing the same thing just by changing the limit. Only this, the argument will going to change according to the this limit. Now, after having this, the knowledge of the Fourier thing, today maybe I don't have that much of time to cover the problem. Maybe in the next class I will going to cover the problem, but before the conclusion of this class, I will also like to mention something. For example, if there is some finite discontinuity, say this is my f x. So, I have some finite discontinuity like this. It is not infinite discontinuity, some finite discontinuity, some point x equal to a. So, the value of this discontinuous point will be the average of the value this. So, this value is nothing but the left hand limit. So, this value, what is the meaning of f a minus? This is limit x tends to a minus epsilon f x, this, and if a plus is equal to limit x tends to whatever the value I have. So, I will have the value here, I will have the value here, and the average is somewhere here. So, f a, the value of f a will be something, if there is some finite discontinuity, should come out in this form in Fourier series. So, these things we will going to apply, or we will show naturally how these things are coming when we deal with some problem, some definite problem. So, today I like to stop here, because if I start the problem I am not going to finish that within this within the time. So, next class we will do some kind of example. We will show how by using this Fourier notation or Fourier coefficients I can expand any given function. So, now one thing you should appreciate about this Fourier transformation, that any function can be represented in terms of the combination of sine and cosine. That is interesting, because sine and cosine not a linear kind of function, not a polynomial kind, this is a sinusoidal function, this is a periodically varying function, all of you know about that. So, now how a function, if it is not a sinusoidally varying function, can be represented by a sine series or cosine series is interesting, but our theorem or our theory suggests that it is really possible. And if I take sufficiently large number of terms which are associated with sine and cos, even though they are sinusoidal by itself, they can form as a combination, as a linear combination, they can form a function which is not sinusoidal at all, which is a state kind of function. So, in the next class I will show some example where you can find this kind of feature, where some kind of straight line kind of function, even that can be represented by the linear combination of these things. Only thing we need to find out the suitable coefficient, that is a0, then an and bm. This kind of coefficients will be associated with the Fourier series. We need to find out how these coefficients are there and how this can be figured out with these things. So, with that, let us conclude this class today. So, in the next class we will start from here by this Fourier thing, and we will solve few problems. We will show that how this kind of problem will be solved if a function is given to you, how you make a Fourier series of this function using the knowledge that is shown in today's class. With that, thank you and see you in the next class.